I bought this Cobra 1500 watt inverter. I got this on eBay, open box basically, for about $40, including wires. Somebody actually bought the name brand wires for this. So it's a total of, I think, $150, $100 for this, $50 for the wires. This has been running for a few months now. This has been running my fridge, and actually I can run my air conditioner off of this. I have a small, the cheapest one you can get at Walmart with the switches. It doesn't actually have the electronic dial. I think it's like $110 or $108 for that air conditioner, and it's roughly 500 watts, give or take. And this will run it. Not only that, this will run the air conditioner and start up the fridge at the same time. However, what this will not do is this will not, with the fridge running, start the air conditioner, because the startup on the air conditioner is just so monstrous. So I actually want to see if I can make this do that. Just very, a couple of simple modifications and see if it's close enough. I think I might be able to get it, maybe with a high battery voltage of like 14.4, I might be able to get it to start the air conditioner with the fridge running. And I think in some circumstances this has done that in the past, but very infrequently. All right, so let's take it apart and see what we got in here. Okay. So I took this inverter apart once before to remove, there's a little beeper there, and this thing would beep constantly. Basically every time the fridge started up, it would beep about low voltage, but it would run, so I just took it out so that this will shut off if it needs to, but it doesn't make noise. A little bit more light here. I noticed when I took this apart, there was an unpopulated capacitor there, and that's why we've taken this apart today. Even if that spot were populated, we can still add a capacitor, maybe on the other side, or maybe just tuck it in somewhere here where it'll fit. I suspect if I add another capacitor there, at least another one, that might be enough for it to start the air conditioner with the fridge running, because I think it's close enough. So this is a 200 volt, 330 microfarad capacitor. So in order to determine if I can add another capacitor there without screwing up the circuit, I have to know what this capacitor does. Is the capacitance important for timing, for example? So let's take a look at this circuit here. So you notice each of these heat sinks has a wire going to it, a high current wire, and we have these little what appear to be perhaps a MOSFET or something like that, but they are not. You notice there's only two legs. So one leg is power in, the other leg is a control, I believe. So these are just basically just little switches that go on and off. And I suppose that would be some sort of a transistor, I suppose. But I don't know what I'm talking about. But anyway, so what this does is these switch on and off, and they put power through these high current leads into this transformer. And so this is basically, this circuit runs independently, and that's what we need. We need this to be independent, and we need to verify that in order to double up this capacitor. So then what this does is this transformer here, they have an output. There's actually two outputs on this transformer. So you see the one, there are those two traces there under my finger, and then we have 1, 2, 3, 4 diodes. This diode here, you see, is not connected to those two traces. That's actually connected to a different two traces back over here, and that's the other side of this transformer. And then we have 1, 2, 3, 4. So it just basically full bridge rectifier, same thing. We have another 8 diodes over here, 2 full bridge rectifiers for the 2 output coils of each of these transformers. These transistors here, they switch on and off, and this functions basically as an automotive coil, and it takes a low voltage DC and it turns it into a high voltage evidently AC, and I'll come back to that. And so then, of course, it rectifies that, and then this capacitor charges up with, 120, 100 some odd volts. And actually, I'd have to put a meter on that. I didn't think to do that. But, and so then this high voltage supply here is then taken over to here, to these two, I want to call them MOSFETs. Of course, I'm probably going to get names wrong, so please roast me in the comments. So this is actually what creates the waveform that your load sees, so to speak. It takes this high voltage and it connects it, alternately positive to here, positive to here, positive to here, and it goes back and forth. This runs at, the 60 hertz, and this is what actually reverses the polarity. So it takes this high voltage supply here, just this storage, which is coming from, this supply here, and it turns it into a very, not very accurate, but reasonably accurate modified sine wave 60 hertz out. This, the voltage and the timing here is a little bit more precise. The frequency supplying this does not matter. This can kind of basically do whatever it wants as long as it generates about 120, 130, 140 some odd volts. So what we're going to do is we're going to go back in time and to when this inverter was still connected, and we're going to verify that this frequency has nothing to do with this here, just to double check and make sure this is operating independently. All right, we're here in the past before I detached this inverter. We're going to fire this up and we're going to see if indeed this frequency is A, higher, and B, potentially the frequency fluctuates with load, which is what we want to see. If the frequency of this high voltage generator actually matches the frequency of the modified sine wave output, we will find that we probably won't be able to modify this to increase the startup load. Let's see. The meter says 60 hertz, even though it's not touching anything, so I imagine, let's see. It's a little bit fadooey, this frequency on this meter. 73 kilohertz. Now it says 120 hertz, and actually I would expect that. I would expect it to say 120 hertz for this because, and actually it says something higher than 120 hertz, but I would expect it to say 120 hertz because the nature of the modified sine, I think it's going to confuse this meter and it's going to see more cycles than there actually is. Let's put this under load and see how that affects things. Okay, 60 watt cold soldering iron. Try not to electrocute myself here. Let's see what this frequency is. 73 kilohertz previously. 26 kilohertz. Okay, so I think this is good. This is what I'm expecting this to be doing. And this is 200 some odd hertz. That's a little bit how do you do, but we don't care, so that's good. I am satisfied. I think we might be able to modify this. By the way, this Cobra, when I bought it, came with the name brand set of wires. The ground wire, just for grounding out the case, was copper-coated aluminum, and I thought, well, just a ground wire, not that big of a deal. And I couldn't remember. I feel like I would have noticed when I put this inverter, installed this inverter, but I didn't. But you can see this giant, like 4-gauge wire is copper-coated aluminum. It's not actually solid copper. So, of course, copper-coated aluminum is a scam. It does not conduct as well as copper. And actually, say, for example, in order to get the conductivity of 10-gauge copper, you need, I think, 8 or 6-gauge copper-coated aluminum. Like, you actually have to have a much larger gauge in order to get the same conductivity. So this, if this was copper, this gauge of wire would be reasonable, but with this being copper-coated aluminum, these wires are actually too small for this inverter. And somebody paid $50. I got this used on eBay. This is a $50 Cobra brand set of wires. So these are name brand, same brand as the inverter. That's a scam. Somebody paid $50 for that. That's a shame. Okay, so we're back to present again. Now, looking on the other side of this, coming back to those transformers, are those AC or are those DC? Okay, so the base of the transformers, all of them are soldered to positive. It doesn't matter, it's, it's all common. So you can see 2 wires in at the top. At the bottom, there's 1 wire out, 2 wires out. So each transformer has 2 wires in the top, 2 high current wires in, 2 high current wires out. Now, all of those high current wires are going to positive, but I believe this is actually, those capacitors actually generate, or excuse me, those transformers actually generate AC. And you can see all of these transistors here operate off of the negative. And so what they're doing is they're switching the negative onto these heat sinks alternatively. So I believe what's happening here is this is a winding in one direction. This is another winding, but this one is wound backwards. What it's able to do is this one on, this one off, this one on, this one off, this one on. And so what it's doing is it's putting the same negative into the transformer in the same direction, but because the windings are reversed, this transformer actually operates at AC, you know, an alternating current. And I think the reason they do that, instead of doing like an automotive coil where it's just, you know, DC and it's just on, off, on, off, well, the reason they actually switch that, I think, is because this operates more efficiently. And I think there isn't on this side, not that I can tell, but if you look on the output, there are these little ceramic capacitors. I believe this might be able to create a bit of a resonance, sort of like how a, I wonder if I can draw that for you. Your automotive coil, you know, this is voltage, this is time, without a condenser. And of course, the condenser, it does prevent arcing at the points, but it also creates a resonance. So without a condenser, what you get is you get a, you know, a doink. That looks terrible. Voltage spike, you know, voltage goes up positive and then comes down to 0, and that's it. However, there's no easy button for clearing that, and I was confused for 20 minutes. So when you have a condenser, what happens is it looks a little bit more like this. Voltage goes up, but then when it comes down, it kind of goes sort of like that. So this peak is the highest, this peak is less high, this peak is smaller, and maybe a tiny little peak over here. So what happens is that a capacitor, it actually creates a resonance. You know, the inductor has an inductive spike, and so it charges the capacitor in this direction. Then the capacitor discharges through that inductor, and then because an inductor resists changes to states of current, the inductor basically has a momentum. The electrons have inertia in the inductor. So once that capacitor is empty, current continues to flow, and then it charges the capacitor backwards in this direction. So then the capacitor discharges again, and so it kind of goes, sort of like dropping a bouncy ball. It goes doink, 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 doink. That's exactly what happens with your coil. So I think what they're doing is, rather than, you know, having one kick, they're kind of kicking it in both directions. So they're giving it the initial kick upward, but then I think instead of, you know, simply letting it fade off there and you know, do something small like that, they're actually giving it another kick in that direction, and so they're kind of kicking the ball and keeping it going, like dribbling a basketball, so it never actually stops. You continue adding power to it, you know, at whatever resonant frequency. I surmise, but it probably is not quite that efficient. But anyway, the other thing that we can see here is these transformers. They have a what looks to be a ferrite core, not an iron core, as far as I can tell. It's possible I'm mistaken, but I suspect that's a ferrite core because ferrite works better with high frequencies, whereas an iron core works better with low frequencies. That's why, for example, microwave oven transformers, they have iron cores. They run at a low frequency, at 60 hertz, and so the iron core is better. I think it has a, I suspect anyway, it has a higher inductance, and so it's more better. However, the iron core, at a higher frequency, the inductance is less. It is less able to, you know, take a magnetic flux at that high frequency, I suspect. And I could be full of shit, feel free to correct me. But I do know that this ferrite operates better at a higher frequency, so I suspect it's able to build up a reasonably large magnetic flux, you know, in it at a high speed, whereas the iron can probably build a higher magnetic flux. It just takes longer. So this works better at a high frequency. And so that's why they're using this, is because this can run at any frequency. So they run it basically as fast as they can to keep it, you know, efficient. They I think they follow the resonance of that sine wave based on the load, and I think the load, you know, changes that sine wave, and so it has to stay on for longer in order to build that a large enough magnetic saturation to get that, you know, a higher current kick on the output and stuff like that. But so I think what we can do, this is 330 and I have 470 microfarad. These are both rated at 200 volts, so that will more than double the capacitance of this high voltage supply. So hopefully that'll help. I don't know why that's unpopulated. I think they had an 1800 watt model of this, so I assume there's minor modifications that they make to this one. Let me put it this way, maybe it won't help if I add a capacitor there, but I don't think it will hurt. So that'll help kind of smooth it out, and it should hopefully, it should be able to handle that high surge for just a tiny bit longer. Hopefully, if it can handle that surge for just long enough for the air conditioner to start spinning, and, you know, build up a little bit of momentum, the current will drop off and we'll see. The other thing that I'm going to do is these are all, I think 16 volt capacitors. Yes, and each one is 3,300 microfarads. And those are simply across the 12 volt side. And let's verify that. And yes, indeed, those capacitors are across here. Positive here, that one's negative. It doesn't matter the polarity, but yeah, so they're just across. I probably won't do anything in here just because there's not a whole lot of room. I have a capacitor bank built out of 16 volt high capacitors, and I'll just put that capacitor bank, I think, just out here, and we'll see if that helps. I need to replace those wires with actual copper instead of copper-coated aluminum. That'll help. That'll reduce voltage drop, so that'll make this thing happier. And the other thing is, I wonder if I can beef up some of these solder traces here. So for example, so this here is the output of the transformer, and then these here 1, 2, 3, 4 diodes that go out here to the supply. So this, this isn't running all the time, but this can theoretically, up to maybe 5 amps, if you think 5 amps here, 5 amps here. So between the two transformers, they output a total of 10 amps on the 120 side. Oh, that's 5 amps. So there's a little bit of opening there. I'll see, maybe I'll beef up that with some solder. I'll certainly beef up some of this because you see right here, this is the bottleneck. These soldered on right here, I believe, are inductors, and I think you can see that. Okay, a couple diodes, but those things there, I don't think those are resistors. I think those are inductors. Okay, so there's 4 MOSFETs here. I can't quite tell what the inner two are doing because some of there are traces on the top and I can't really see what's going on. I'm just having difficulty seeing the traces. But it looks like for these outer two, let's see. So for example, this MOSFET here, we have base, collector, and emitter. So this is the control side. This is the input to the MOSFET, and this is the output to AC. And you can see this wire right here. That's AC. That middle there is the output of the MOSFET. Input is right here. So what happens is, this is the high voltage DC. There are 4 inductors in series, with this MOSFET. So the 4 inductors are what connect this high voltage DC to the input of the MOSFET, and then the MOSFET, outputs to AC. Whereas this other one, this first one, the other one I can see where it's going. It looks like this is the output here, and you can see there's the other AC wire, kind of right there. So this is the output. This is the input here from the other DC side. It looks like there are no inductors in series, and then that's the base or the control right there. And then these two middle ones I can't quite tell. So it's weird. Some of these inductors are in series, and I think that's somewhat to smooth out the AC, maybe. I'm not entirely sure. Anyways, you can see here, I'm cannibalizing this capacitor from the Make Sky Blue solar charge controller. I have 2 of these things. Both of them don't work correctly. One of them was just a replacement board that was sent to me in an attempt to make the thing work. These do technically work. It is an MPPT solar controller, and it does do that, but I mean, if you fart too loudly, they quit working. They're very, very delicate. So let's go. Solder certainly isn't the most conductive thing in the world, but it is better than nothing, so that should be a minor improvement. Let's see if it even still turns on. Nice, 12.6. So I have here AC voltmeter, and I have the blower on this swamp cooler. Should draw, I think, 40 amps at the 12 volt side, I want to say. Let's see. Fires right up. 13 volts. It looks pretty good. I mean, it's working. So when you turn that off via the button and then turn it back on, it ramps up. Let's see if it will still ramp. It seemed like a ramp, but this showed constant voltage, so I guess that might have just been the motor speeding up, but yeah. Now, we're going to measure frequency with and without load with this second capacitor and see if and how that has changed. So same setup as before, same two shitty wires. Fridge is off, lights are off, and the soldering iron, by the way, it is a 1960 soldering iron, so it is not a positive temperature coefficient soldering iron. The proprietary name for this is Magnestat temperature controlled, but basically what this does is this draws a constant 60 watts until it reaches temperature, and then a little relay in here shuts off power completely. So it's a constant 60 watt load from cold, and it is cold now. Unloaded frequency, and now this says 59.8 hertz. It said 60 before, just open circuit, but of course probably means nothing. 72 kilohertz. It previously was 73 kilohertz. The lower frequency would lead me to believe that this is under a slightly higher load in standby mode, which is interesting. Could also be, I think the voltage might be a tiny bit higher, but not by much. Now we plug in cold soldering iron, and I believe last time was 26 kilohertz and 26.64. Interesting. I went back and checked the footage. Last time was 26.56 kilohertz with the soldering iron. This time is 26.64. Now we know no load, the frequency is higher, 76, and then the frequency drops to 26 kilohertz when we put on a load. So with it being 26.64, that is higher than 26.56. That would lead me to believe the high voltage supply on this inverter is under slightly less load with the soldering iron plugged in. So I think it's a tiny bit more efficient. I don't know. There's a lot. Of course, there's a lot unanswered here. There's a lot of variables, but based solely on those two numbers, I'm led to believe at standby this will draw slightly more power, and then with the soldering iron on, will draw slightly less power. But ultimate question: let us see if we can, do anything with the air conditioner with the fridge on. That should tell us. By the way, I think that lower frequency and theoretically higher efficiency is not because of that capacitor. The single 330 microfarad capacitor is enough to run a theoretically 1500 watt load. So a 60 watt load is by comparison very small. There should be plenty of capacitance available. I think the lower frequency is actually because we beefed up all those traces with soldered. We actually put copper in there. So I think it's the extra the decreased voltage drop and all that is actually what increased the efficiency of this a little bit. Okay, battery voltage is 12.8. Everything else is turned off. I don't think my batteries are charged enough for this to work. I suspect with a slightly higher battery voltage, this has potential. If the air conditioner starts with the fridge on with the batteries in this state, I will pee my pants. All right, fridge is running. Of course, 11.8. Starting capacitor shuts off. 12.5, that's not terrible. For those playing along at home, 110 volts AC, 12.5 volts battery. Let's fire up the air conditioner in the lowest setting. Moment of truth. Nope. So what happened is it, and of course the fridge is now pissed. What happened is, of course, it was too much. This thing shut off. Then what it is it ramped up, and then the air conditioner started. The fridge was actually, the compressor in the fridge stalled, and so the fridge is going to be in a perpetual stall state for a couple seconds until the switch automatically opens and shuts off the fridge, and then it'll wait to cool off, and the fridge will switch back on automatically. So just for shits and giggles, let's run the air conditioner. I'll try this again tomorrow with solar panels and a higher battery voltage, but let's just go ahead. Yes, this would not start the air conditioner. Switched it on, and it went into overload, and then it ramped up, and then the air conditioner started in the ramp. So I think it's my battery is too low. I think this will start the air conditioner from a dead stop with a higher battery voltage. So far it looks like not a whole lot of improvement has been made. 117 volts, the voltage usually goes up under load. I get a battery charger on, so the battery voltage was just at 15.2. The fridge just kicked in. Give it a second, because the startup on the fridge is a little bit high, so just make sure the battery voltages come up as far as it's going to come up. Okay, I think the voltage was originally 13.2. I think you saw that on camera, went up to 13.4. Now we're at 13.6. That's probably as far as it's going to come up, and also I'm impatient and hot. Will it start the air conditioner with the fridge running? Moment of truth. Did that modification work? Was that an effective use of my time? Is this inverter? Okay, all right, enough holding. Oh my Jesus God. Oh, it didn't shut off. AC started with fridge running. I am a god. I am Jesus Christ. Like, most importantly, subscribe. Maybe leave a comment. Mostly just subscribe. And hopefully I will do something that works this well again in the future. Just in case you're wondering, the air conditioner started again with the fridge running at 12.9 volts. And I'm here 8 months in the future. I replaced the cables on this inverter. Those are 1-aught oxygen-free copper. They're tin-plated or something. That's why they appear to be, silver and not copper-colored. So these have made a huge difference in the voltage drop. You know, these aluminum cables, they used to get warm to the touch with the air conditioner running. So this has made a massive improvement. So this, I'm sure, plus the modifications that I made. And the other thing, of course, is I have a lot more batteries now than I did. So you see, there's a reverse osmosis tank. That is so that the water pump isn't switching on and off constantly when I run the swamp cooler. That's just so that, it'll cycle, every 10 minutes or something. I got kind of a central battery here. It just coincidentally happens to be the first battery I threw in the system. And I do that so that, I want as few things daisy-chained as possible, to minimize the voltage drop. You can't really see it very well with, all this in place. I'll show you a picture of all these batteries and what they look like. The picture's a tiny bit out of date. I have updated a couple of cables since the picture was taken, but that'll give you an idea of what that battery bank looks like. And then as soon as this fridge switches on, and I have the laptop charging, and the laptop is just dead, because I was just editing this very video that you are watching. So with those two loads, I'll actually switch on the air conditioner. At 12.6, then the fridge just started, and it was at 12.6, it just went down to 12.5, so very little voltage drop. Hit the button, air conditioner starts, 12.4. The AC starts consistently and reliably, so there you go. Now we're down to 12.3. And it'll stay at 12.3 for a very long time, before it decreases to 12.2. So I've been running this system at a loss with the air conditioning for the past couple of days because I still have more solar panels in the mail, but yeah. All right, make sure you subscribe.
So this is super crazy dangerous. That right there is Balin the Mia, and we are going to do something really stupid today. It was a terrible idea. Balin might die. It was making me uncomfortable. Go, Balin!
You riding this?
What the fuck is happening?
Balin said not to talk crap about this camera. It's a piece of shit.
This is so unbelievably sketchy. Why would you put me through this, you jerk?
That's the power of really old engineering.
It'd be nice if it didn't kill me. It's not required.
I felt that fucking pop.
Make a wish, everyone. Make a wish. Not okay. You went too far.
This guy, man. This guy.